Hi, today we'll talk about the bulk modulus of elasticity of fluids. It's easy to understand what happens to solids. Most of us remember this equipment used for measuring its value in laboratories. We look at what happens when, say, a steel bar is strained and get a curve that looks like this. There's an initial stage, known as elastic stage, in which Hooke's law can be used. The modulus of elasticity is defined at this stage. But things are not so easy when we deal with water. What can we do in this situation? But first, let me introduce myself. My name is Marcus. I'm a retired professor of hydraulics. Now, I'm a consultant engineer of many companies that deal with hydraulics applied to sanitation works. Well, there is a way to measure the elasticity of water. But we must think about it volumetrically. Let's put it inside this cylinder and place a piston above it. Now, if we pull up the piston, a negative pressure will start to form over the water surface and water vapor will start to appear. It won't work this way. Okay, if we can't pull up, we can push down the piston. Let's see what happens then. When the force F is applied, water will be compressed, so the piston will move a small distance d, and there will be a small decrease delta V on the water's initial volume V. Let's redraw it using delta instead of d, and the differential terms dF and dV. The corresponding value for the pressure is dF over A, and this is the expression for the bulk modulus of elasticity of water. It's the same used for all fluids in general. Observe that when P increases, V decreases, which means that dV is negative. It explains the existence of this negative sign in the expression. The bulk modulus of elasticity of water is approximately 2.2 gigapascals. This figure shows a water column. Its height is 100 meters. And here is the expression for the modulus of elasticity. Let's rewrite the expression and substitute the values. And we find that the relative reduction of the water volume at its base is only 0.0045, which means 0.45%. It means that for most practical purposes, water is incompressible. Watch out! Is it really incompressible? Well, as we said, for most practical purposes, water is incompressible. But there are important practical cases where it will be necessary to take the water elasticity into account, such as in the water hammer phenomenon. Now let's see what happens with the air. As we know, transformation in gases can be expressed by this equation. It describes a polytropic process, so the exponent n is named polytropic index. When the transformation is isobaric, the exponent n is 0, so we can find that P is constant, as it should be. Take a look at its corresponding curve in this graph. When the transformation is isothermal, the exponent n is 1, so we find that P times V is constant. Take a look at its corresponding curve in the graph. When the transformation is isometric, the exponent n tends to the infinite, so we find that V is constant. Take a look at its corresponding curve in the graph. When the transformation is adiabatic, the exponent n is equal to k, which is equal to Cp over Cv. If you don't remember, Cp is the specific heat of the gas at constant pressure, and Cv is the specific heat of the gas at constant volume. There's a video about this topic in our channel. I'll leave its link in the description. So, this is the equation that prevails. Take a look at its corresponding curve in the graph. Let's rewrite the gases equation and find its derivative. We rewrite it, and again, and another time, and we find this expression that shows that the modulus of elasticity of a gas is equal to the pressure times the index n. So here is our equation, here are the polytropic indexes, and here are the values of the elasticity modulus for each gas transformation. In practice, since our studies are applied to atmospheric air, the polytropic index corresponding to a diabatic transformation is 1.4. So, it's important for us to know that liquids, such as water, have elasticity modulus values that remain constant for practical purposes. On the other hand, gases have elasticity modulus values that vary with the pressure and the transformation type to which it is submitted. When we study water hammer, the elasticity modulus of water will be important for the determination of the so-called celerity, and the elasticity modulus of the air will be important for studying the air chambers. But these are topics for other videos that will come soon. See ya! Oh, and if you like this video, don't forget to give it a like, comment, share, and subscribe. Hit the bell so you can be notified of my next videos.